Hello everyone, welcome to our Lab 2 design presentation, brought to you by Ata, Faraz, Menksha and Mustafa. In this video, we will first touch upon the purpose of our lab, and we will also be taking you through a product overview, a review for Lab 1, the problems that occurred in this lab, the solutions we chose to implement, as well as the metric and results after the implementation of these solutions. In Lab 1, we were given the task of creating a production line for the assembly of tape measures. We were required to meet a demand of 6,000 tape measures per week. Our group was to achieve this as efficiently as possible while minimizing the number of defective items. To accomplish this, our group had to plan out how the tasks were to be divided into workstations, and by determining task times along with utilizing methods learned in the course to optimize our assembly setup.
The end product of the assembly line is a certified 16-foot orange tape measure that displays both metric and SAE measurements. The product is consisted of 6 distinct components, such as 2 halves of the outer plastic cover, the tape measure blade, the black stopper, the white plastic blade guide, the 3 unique screws that fall into their specific holes, as well as the metal clip. After completing Design Lab 1, our group was able to identify 3 key production issues that were weighing down the flow of our assembly line. These issues consisted of screw fastening, identification and placement, as well as the final build quality of the product. The first problem was the identification and placement of the screws in their proper positions. We found that there was an excess amount of idle time due to an increased load on the cognitive portion of the worker's task. We found that the worker was placing the wrong screw in the wrong location, which was creating excess amount of idle time that could be significantly reduced.
The solution that we developed for our first problem was that instead of having a blank cover, we would label each hole to its corresponding screw. The holes were labeled 1 to 3, and that matched with the different screw sizes. The different screws were put into bins, and the bins were labeled A, B, and C. This solution was simple to implement, as it had virtually no cost added to the production setup.
After implementing the first solution, the location of the holes on the tape measure were labeled with the corresponding screw. Labels were also placed on the bins that contain the screws so they are more identifiable by the worker. Another outcome of this solution was that the worker had increased control over screw placement, helping to reduce the time to fasten the screws, as well as matching the correct screw to hole. The difference in time between Lab 1 and Design Lab 2 was found to be 11.2 seconds, ultimately improving workstation cycle time.
The second problem that we identified was that the speed at which the screws were fastened was not efficient for our desired workstation time. We noticed that when the worker was fastening the screws manually, it was taking a significant amount of time in proportion to the takt time. In addition, it was also noted that the fastening of the screws manually incurred fatigue on the worker's wrist over time. Since the worker had to keep fastening one product after another, their performance was decreasing.
Our solution for this problem was to implement an electric screwdriver or a drill instead of using an ordinary screwdriver. This solution generated a time of 24.3 seconds to complete the fastening of all screws, as well as the metal belt clip. The outcome for our second proposed solution was that we were able to drastically reduce the speed at which we complete the tasks. In Design Lab 1, we recorded a time of 48.6 seconds, and after implementing our solution, we were able to record a time of 24.3 seconds, a difference of precisely half. This also decreases worker fatigue, along with the risk of work-related injury. Another benefit is that all screws are tightened to an equal torque, increasing product quality. Overall, we were able to increase our production flow by 24.3 seconds, ultimately succeeding in solving this specific efficiency problem.
The third problem we addressed was the overall build quality of some of the parts. The first issue we encountered was aligning the spring with the winding stem. This issue was prevalent especially when trying to do so in a fast-paced environment. Most times, the spring would be in a position where it is hard for the worker to grab and position it properly. Also, the white plastic blade guide was difficult to position into the base of the tape measure. Often than not, the worker would have to fiddle around with the piece in order to find the proper orientation at which it should be installed. We also noticed that the build quality of the piece was subpar, as it sometimes would break during installation.
The first part of the third solution implemented was to introduce a tool to increase the precision at which the worker places the spring in the winding stem. Considering the spring is quite thin, this resulted in an issue where the worker could not place their fingers inside of the housing to position the spring onto the stem. To solve this issue, we issued the worker with industrial tweezers to increase the precision of the spring installation. The second part of the third solution was to color code the base of the plastic cover to mark the location for where to insert the white blade guide. We also color coded the side of the component so that it coincides with the marked location on the outer cover. The outcome of solution 3A was that we were able to decrease cognitive idle time and increase the precision of inserting the spring into the winding stem. By using a tool, we were able to eliminate the risk of injury because the worker does not have to work with a sharp metal blade. We were also able to reduce our workstation time from our initial time of 14.5 seconds to our reduced time of 6.6 seconds. After adding a location identifier to the white piece, we were able to reduce worker error as well as increase ease of part handling, which ultimately leads to the reduction in placement error. Some of the solutions that we were not able to implement were a screw dispenser, higher quality screws, uniform screws, and reduced malleability of the metal spring. We wanted to incorporate a screw dispenser into each workstation to increase the speed at which the worker selects the screw to the corresponding location. The second non-implemented solution was to use higher quality screws that had a harder strength and were also magnetic, allowing for the worker to use his tool to pick up the small screw instead of his hands, reducing placement error and increasing ease of handling as well as wear and tear on the screws. The third solution was to introduce uniform screws. This would reduce the cognitive effort performed by the worker as opposed to trying to match each screw to its correct position. This would help increase the placement and tighter fastening of the screws. The final solution was to reduce the malleability of the metal spring to help maintain its structural integrity. This would allow for ease of placement by the worker, thus reducing any excess workstation cycle time required to correctly position it into the winding stem.
The management process that we implemented is the theory of constraints, or TOC. TOC focuses on the system bottleneck because each system has at least one constraint that is holding the production flow back. The 5 steps that TOC uses is to identify the constraint, decide how to exploit the constraint, subordinate the bottleneck, and elevate the bottleneck, and repeat if necessary.
To apply this management process, we started at step 1 by identifying the bottleneck. In this case, our bottleneck was workstation 3, where fastening the screws constrained our production flow, as that task took 23.3 seconds. Looking at step 2, we decided to implement an electric drill in order to speed up the fastening process. We then moved to our third step, which was to subordinate the bottleneck. We did this by measuring the increased efficiency due to adding an electric drill to replace the manual screwdriver. This ultimately reduced the slack that was in front of the bottleneck and standardized our output. And finally, the last step was to elevate the bottleneck. We did this by training the worker on how to operate the drill. These improvements do require an investment, but ultimately helped increase the efficiency of our assembly line.
To summarize, our presentation's overall goal was to improve the flow of our assembly line given the practical issues that we found in Design Lab 1. Our first issue was the identification and placement of the screws. We solved this by labeling the screws and the corresponding location on the product. Our second problem that was identified was the speed at which the worker fastened the screw to the cover. Our solution to this was to introduce electric drill to increase the efficiency at which the worker fastens the screws. Our third issue that we tackled was the build quality of some of the parts. Our solution to this was to introduce a tool to increase precision placement as well as handling safety. The second solution that we deduced was to mark the bottom half of the white plastic blade guide in correspondence to the proper orientation of the base. This was important because we found before we implemented this, our tape measure was not meeting efficiency standards and build quality. In summary, for our first problem, we started with a time of 38.5 seconds, and after implementing our solution, we could reduce our time by 11.2 seconds to a final time of 27.3 seconds. Our second issue had an initial time of 48.6 seconds, and after implementing the electric drill, we could reduce the workstation cycle time and combine two workstations together to a time of 24.3 seconds. The last